Talked about how action potentials are generated. I've talked about how action potentials are sent from one cell to another. Now I want to talk about how do we actually connect neurons to make things happen. So we're going to use neurons to make neural circuits to mimic the kinds of things that are going on in animals so that you'll be able to propose, given a particular input, a sensory input such as a taste or a smell or an image, how might that cause a change in behavior? And neural circuits are a central part of how that happens. So first you need the pieces. If we talked about a typical cell, a typical neuron, we often draw them like this, with a lot of branching dendrites, and these would themselves branch until we had ends on them. There would be a cell body with a nucleus, so here's the nucleus. These are dendrites. And information flow is going this way. So synapses are on, from other cells, are on these dendrites. Okay, synapses from other cells, from other neurons, would be on those dendrites. Synapses can also be on cell bodies. So all of these would be from different neurons. Some could be from the same neuron, but mostly from different neurons on dendrites or the cell body. And then the cell body has one axon that in turn can have many branches. And each of those branches ends in synapses. Those synapses can be on other neurons, or they can be on, for example, muscles. Okay, so here's an ugly neuron with dendrites, a cell body, and an axon. And in a typical neuron, we usually think of the dendrites as not producing action potentials. The action potential is happening here. It starts here. And it only happens if you get enough positive charge in that location from all the synapses. So imagine that we have a synapse where we have some positive charge coming in, and maybe another synapse that's opening potassium channels. So potassium is leaving, and that would be negative. All of that charge disperses, and you get an action potential if the sum of all of it, summation, if the sum gets you to minus 45 millivolts. Okay. If all of those charges put together get to minus 45 millivolts, we get a new action potential. Okay, this would be a typical neuron, but I have to show you one exception. Lots of sensory neurons, have processes out here with receptors on them. They might be for odor, they might be stretch channels, and of course lots of branches, all joining, and they're starting an action potential here. Very often the structure is a little different. They have a cell body with the neuron here, and then branching out to their various axon terminals at the end. And so on these, you get the action potential starting somewhere back here. And so this now is the spike or action potential initiating region. Okay, and when we're talking about neural circuits, when we're talking about how this works, I want to go back to this image. And when we talk about summation, we often talk about spatial summation, in other words, from different regions. So the example I showed you before is spatial summation of these two synapses active, one positive, one negative, and the sum is whatever they all add up to when we get to this point. You can also have temporal summation, temporal summation. Imagine that one of these has action potentials over and over again. So action potentials, AP after AP, so many action potentials, so much that each new action potential brings in more charge, and it doesn't have time to dissipate. Now all of that could add up, even though one action potential might not get you a new action potential. One action potential in our green axon here might not get you enough positive charge for a new action potential. 10 in a row in the span of a tenth of a second or a fifth of a second might be enough to do it. That's temporal summation. So spatial, two different locations or more at the same time. Temporal, one axon releasing a neurotransmitter over and over.